failure and deformation, right? Okay, so you need to differentiate these two. So for the failure, normally categorized by having the what you call the shear strength, using shear strength parameters, and for the deformation, normally we will use the stiffness, okay, to describe the behavior. I mean the deformation. Okay. So I start. Okay, we will talk about the elastic stress strain for the beginning. So you still remember the elastic materials. You just need two parameters to describe this behavior, which is a linear elastic material. This is linear elastic material because you can see a linear straight line here, right? So the slope is actually the modulus, Young modulus. Okay, so this is mu. Is actually the Poisson ratio, which is the horizontal strain over the horizon, over the vertical strain. Okay. So elastic strain, if you want to describe in a three-dimensional space, you can use Hooke's law. Okay, we will talk about Hooke's law later on, but now we look at the relationships first. When a material is subjected to stresses, it undergoes strain. Okay, the ratio of the stress experienced by the material at the point to the strain that it incurs is known as a modulus. Okay, so we have a different modulus for different loadings and different boundary conditions. Okay, so if you have the modulus of material, then if you know the stress, then you can find the strain, right? If you know the modulus, and this modulus can be different or different under different boundary condition and also under different type of loading. So my question is, how many modulus you have learned? If you still remember the chapter 1, the document that I give you and ask you to study. Okay, chapter 1.0, the lecture notes 1.0. There are few types of modulus. Anyone can tell me what are the modulus? You have learned how many modulus? Okay, the basic one is Young modulus, right? Other than Young modulus, what other modulus you have? Anyone?
Elastic modulus.
Okay, elastic modulus will give you a Young modulus. Okay, so Young modulus normally refer to elastic modulus. Okay, other than this Young modulus, what other kind of modulus you have?
Secant modulus.
Secant. Okay, secant modulus itself is another term. Okay, we can have a secant modulus. A secant modulus is still the Young modulus. Okay, but the slope that we calculate is from a different point. Okay, it's still considered Young modulus. Like secant modulus, tangent modulus, okay, initial modulus, they are all considered as Young modulus. Okay.
Sir, what about shear modulus or bulk modulus?
Yes, this is correct. Shear modulus, okay, under shear stress. Okay, bulk modulus under the this what called all-rounded stresses. Okay, and then apa lagi?
Bulk modulus.
Yeah, bulk modulus, shear stress, shear modulus. Another one.
Triaxial Young modulus.
Okay, this consider Young modulus also. Okay, what else?
Constraint modulus, sir.
Yeah,
Modulus of rigidity.
Sorry.
Modulus of rigidity.
No, not this one. Okay, just now your friend has answered that. The other one is constraint modulus. Okay, constraint modulus is a very common modulus that we use for practical. Okay, constraint modulus normally we obtain from odometer test. Okay, under confined condition, confined boundary condition. Okay, constraint modulus. So all these modulus can be actually described using the Poisson ratio. Okay, it's all connected. Okay, if the soil is elastic, these all materials can be calculated from each other. Let's say you want to get the shear modulus, you can get it from the Young modulus and also from the Poisson ratio. Okay, so basically, for elastic soil, the obtain of the modulus is very simple, very straightforward. But if the soil is not it's not elastic, then the modulus can be quite tough to get, okay? Especially you have a non-linear behavior. Okay. So the most common modulus that we learn is actually the Young modulus for the linear elastic material, and these linear elastic materials can be described using Hooke's law. Okay, the most simple model, okay, or we can say model because Hooke's law actually describes the linear elastic material. Okay, so basically when there is you apply the stress, then you have an increment of stress linearly. So let's say you pull a bar, then it will elongated linearly, and but up to one point, this point normally is what you call a fracture point. You break, okay, fracture point. But however, the Hooke's law itself does not tell you where is the failure point. Okay, but in reality, the material will fail, and then even if it is an elastic material, it will have a failure point. But if you use the Hooke's law, it won't tell you where is the failure, okay, because it's actually the straight line. Okay, you pull this bar, okay, you go straight only. You look, the line is linear elastic line, because elastic means that after you release the force, it will go back to its original place. So it's elastic. Okay, so it has no yielding. There's no failure there. Okay, you keep elongated. However, the real soil or real material is not like that. You fracture, you break. Okay, even though it is elastic material, there must be some fracture point here. But Hooke's law, if you use Hooke's law, it will tell you the behavior of linear elastic. So the slope for this line is the modulus, the Young modulus. We call it Young modulus. So basically, it's a stress over strain. Stress over strain. Okay, so Hooke's law can give you, the relationship for three-dimensional space. So we are going to look at how to obtain the called the stress strain for three-dimensional coordinate system. If you look at here, let's say this is a material subject to the sigma x, which is the normal stress at x directions. So the other directions, we have a zero stress, and then under this direction, the strain in x direction is sigma x over E, and the strain for the y direction, then there's a Poisson ratio involved here. Okay, Poisson ratio here, and for the z also same. There's a Poisson ratio here. So meaning that when we subject these materials under the loading at the x direction, we can get strain at different direction. Okay, similarly for sigma y, normal stress at the y direction, we have a strain y equal to stress sigma y over E, and this is epsilon x in the y under the loading y in the direction of y, epsilon z, okay, and then finally is sigma z, which cause this field three types of strain also. So all these strain actually we can actually combine together. So the epsilon x is actually the summation of all these stresses, and then so if you have a sigma x, sigma y, and sigma z, then you will know the combination effect of all these stresses and the result. So same to this epsilon y and epsilon z. And other than the normal stress, we also have a shear stress. Sometimes we apply shear stress to a material, and this shear stress will cause a shear strain. So this is how to get the shear strain from the shear stress, but we did the shear modulus here. Okay, shear modulus to describe this, to tell you what is the shear strain. Okay. So after we get all this expression, then we combine it together. We write in terms of this metric form. We write in metric forms, then you will get this expression. So you have seen, I think you have seen this quite many times. You have learned the materials before, so you should know this. Okay, so if you want to get this the strain, you want to get the strain, you need this is materials properties itself, material properties, which is Young modulus and Poisson ratio, and shear stress, shear modulus, sorry, shear modulus. With these properties and the subjected stress applied on the material, then you can get the strain. So you can write in different form. Okay? If you have a strain, the material properties, you also can get the stress. Okay? Or you can write in another form using the bulk modulus, also can. Okay? Because bulk modulus is related to the Young modulus also in this form. Okay? So this is the matrix form for the bulk modulus. Okay. So this is quite common and very common for the elastic material. It's very common in our civil engineering use for, let's say, for steel, right, for concrete. Okay, we use quite often the elastic materials, but not so often to describe the soil, because the soil is more like non-elastic, and it has a failure which is easier to achieve, because the failure point for the soil is actually much lower than the steel and the concrete, right? So, and beside that, the soil mostly behave non-linearly, so that's why the Hooke's law cannot apply to soil. And now, this slide talk about the two-dimensional problems. Okay, if you use the finite element numerical modeling, okay, you can use a 2D analysis, 3D analysis. Okay, 3D analysis is quite complicated, and it requires a lot of computational effort and also resources. So it will take your time, and also your computer space, also your RAM. So you need a powerful computer to run three-dimensional problems. Okay, to run this three-dimensional analysis. So that's why the two-dimensional analysis is still very common, and it has an advantage over this three-dimensional analysis. Okay, there are two types of 2D. There are two common types of two-dimensional problems, which is the plane stress and plane strain problem. Okay, so if you perform the plane stress analysis, okay, then we know that it is a 2D analysis, same as a plane strain. Also, it's a 2D analysis. And another 2D analysis is asymmetry analysis, asymmetry. Okay, so we have plane strain, plane stress, and asymmetry, which is a very common two-dimensional analysis for two-dimensional problems. Okay, even though we know that the actual problems in the real case is always three-dimensional, right? But we can simplify into the two-dimensional problems. Okay, for example, in geotechnical, right, we have embankment. Okay, embankment normally is very long embankment. Okay, long embankment, and then strip footing also long strip footing, right? Okay, tunnel also long tunnel. You can see. So we can use a two-dimensional analysis, okay, to perform this numerical modeling for these 2D problems. Okay, that analysis, we call it plane strain analysis. Okay, for long structure. Okay, but another one is called plane stress. Plane stress. Okay, plane stress analysis is for the normally for thin, very thin structure, thin structures. Okay, like a plate, thin plate. So in this analysis, plane stress analysis, there are two assumptions that we made, and not two assumptions, but one assumption, and which is the sigma z, meaning that the stress in the z direction is all zero. In this direction is the direction that face into the page. I mean, let's say x, x is a horizontal direction, right? Y is the vertical direction, and z is the one that towards you. So there's z direction. So when the stress is zero, okay, to together with the shear stress also 0, then we can simplify the previous form, matrix form. Then you do some mathematics. Okay, we put everything 0 here into the matrix form. This matrix forms we put 0. Okay, here let's say we're supposed to use this one. Okay, use we put stress, right? Stress equal to 0. This one also equal to 0. Then eventually you will get something like this. Okay? You get something like this. So in plane stress analysis, this is the stresses that we can find. Okay, and this is the strain, which is the input. In this case, this is the input. But you can write it also the terbalik dia, no problem. You can write the terbalik dia, no problem. Okay, so you just need to simplify it by substitute the sigma z, tau, tau yz, tau sz into this form. Okay. So this is a plane stress analysis, commonly, you see, often applied to problems relating to thin plate and structural member, wherein our plane stresses cannot build up. Okay. So in this case, the stress only happen in the x and y direction, but not z direction. Okay. Structure yang nipis, structure yang nipis. So this is quite common. If you study numerical modeling, finite element, I think you will learn this. And then for plane strain analysis, okay, is where we have a condition S1x equal to 0, or other the shear strain also 0. Okay, this is related to strain. Okay, related to strain. So all these parameters is 0. Then you input into the earlier matrix form. Then you will get this. Okay, you will get this simple matrix form. So with this epsilon, okay, we have epsilon value here with the parameters, metric parameters, then we can get the stress. Right? Atau terbalik, okay. Okay, plane strain conditions are commonly encountered in problems which involve great length in the outward plane direction, like tunnel, retaining wall. Okay, that's how I also mentioned embankment, and then also mentioned the box strict footing. Okay, many geotechnical problems fall into this category. So, for geotechnical design, plane strain analysis is quite common. We always assume the problem is 2D, two-dimensional. Right? It's two-dimensional. You still remember how you design for the retaining wall? We also assume that the wall is long wall, right? Okay, this is about the plane strain analysis. Any questions so far?
No, sir.
No, sir.
Okay, now we move to another small topic here, or more to like understanding of effective stress. And you have learned this before, but now I try to reinforce your understanding on the effective stress. You know the total stress is equal to, effective stress is total stress minus Paul water pressure, right? Okay, I think you remember that. But you have to remember also the effective stress can be in a different direction, same as a total stress. It can be in X, Y, and Z direction. And this effective stress equal to total stress minus Paul pressure is always valid. Okay, no matter in what direction, it's all correct. Okay, so you can see here effective stress even in X or Y or Z directions. You just need to take the total stress minus Paul water pressure. This is valid because the Paul water pressure, okay, is hydrostatic pressure. Even this is not hydrostatic, but the Paul water pressure itself is all-rounded pressure. Okay, all-rounded pressure. So the pressure in X and Y, Z direction is all the same for water, right? For water, Paul pressure. And then you look at this part, the tau, the shear stress. The shear stress total stress and effective stress for shear stress is the same. Okay. Bila letak prime atas ada macam nokta, this is prime. Okay. So tau prime and tau. So yang tak ada prime tu maksudnya ada total stress. Okay. Kalau tengok atas tau, this is total stress, this is effective stress. Okay. So total stress is what? Is how to get total stress? You take unit weight times depth, right? And the depth. So gamma times z, right? If the soil is saturated, you take gamma saturated. Gamma saturated minus pore pressure, then you get the effective stress. Or you can take gamma prime times z, then also same, you get the effective stress. In gamma prime is gamma saturated minus the pore pressure. Okay. In soil mechanics, a saturated soil is considered to be comprised of two phases: pore water and soil skeleton. Okay. If the soil is not saturated, then you will have another phase, which is air. We can consider the effective stress to be a quantity which categorizes the contact force between the soil grains in the soil skeleton. So in this context, the term soil skeleton refers to the assemblage of soil grains. So you can see there's a contact force between the soil grain, and because the soil grain is the particle, so you can measure this the contact force between the grains. The contact force. So we call it effective stress. Okay, and this effective stress is related to the weight of the material. Okay, so that's why you take the unit weight times the depth. Okay. So the deeper the soil is, then you have higher effective stress. In general, the higher the effective stress, sigma xyz, effective stress for the sigma xyz direction, the higher are the contact force between the soil particles, and thus the higher is the frictional resistance this soil particle have against relative sliding. So when effective stress is higher, okay, then you will get the higher contact force, and then you will get a higher frictional resistance. Meaning that if the soil is highly compacted or very densely, because it is at the very bottom, at the bottom of the soil layer, at the bottom, then it's compacted. So you can see that the particles actually are touching each other quite closely. Then you want to fill the soil, it's more difficult, okay? Because the frictional resistance is higher. Okay? If the arrangement of the particles is very dense, right? So the frictional resistance of the soil particles against sliding is categorized in terms by its shear strength. Okay. So when we talk about frictional resistance, usually we mean shear strength. Shear strength. The strength to resist against the sliding, that's shear strength. Hence, the higher the effective stress, the higher is the shear strength. Okay, remember that. Okay. So that's why when the soil get deeper, okay, I mean the same type of soil, not different kind of soil, the same kind of soil, same type of soil. Let's say it is a soft soil. So the soft soil on top or near to the surface is normally has a lower shear strength compared to the deeper soil layer. I mean deeper depth. When the depth go deeper, the shear strength increase. Okay? This one you need to remember. It's hardly you find that the soil strength is homogeneous. Okay? Atas bawah semua sama. Jarang sekali. Okay? Most of the time you find that the strength, the shear strength is actually increasing. Okay? For the soil deeper into the ground. Okay, later on we'll go talk a little bit more about this. Okay, the shear strength of a soil is not a constant. Right? You need to remember the shear strength of the soil is not constant, even for the same type of soil. Okay, so I mentioned that the strength of the soil is actually increasing when the soil go deeper. For now, it's important to understand the different connotation or definition of the term shear strength. Okay, later on we'll talk about the different connotation definition of shear strength. So the difference between shear strength and effective stress strength. Okay, shear strength and also about effective stress strength parameters. Okay, we'll talk about the strength parameter. Okay, you learned that before. You still remember Cm prime is the parameter for to describe the shear strength. And Cm, right? C is cohesion, I is a friction angle, right? How shear strength is influenced by drainage condition during the shear strength process. Okay, we'll talk about this also later on in the following slide. When dealing with shear strength, most textbook and design manuals speaks in terms of the shear strength parameter P prime and C prime. So this I call it phi. Sometimes you can call it pi also. P prime and C prime. So the shear strength parameters phi prime and C prime are not necessarily unique for soil. Even if it is a same type of soil, but if the soil is subjected to different stress history, then you will get a different value also for the C and V. Okay, so let's say the soil is over-consolidated soil, then the friction angle is higher in the over-consolidated soil compared to normal consolidated soil. Okay, we talk about the clay Okay, if the soil is sand, then you look at the density, relative density. So if the soil is highly compacted or high dense, I mean the arrangement is very dense, then you have a higher shear strength value in the friction angle is higher. In order that the friction angle and the C or cohesion parameters obtained from the lab test are similar to those that exist in the field, it is important that the lab tests are carried out on undisturbed soil sample, which are subjected to initial cell pressure that are similar to those in the field. Okay, cell pressure is also called confining pressure or confining stress. Okay, you still remember in the geotechnic, okay, you've learned about the disturbed sample and undisturbed sample, right? So you want to get the shear strength parameter, you need undisturbed soil sample. Okay, we bring this undisturbed soil sample, okay, to the lab, and then we test. Let's say you use the Tri-Shear test to test. So we need to consolidate the sample. If you conduct the CU test or CD test, and we need to consolidate the soil sample. Okay, so the pressure that we apply to consolidate the soil sample so that it will represent the actual effective stress in the ground, right? So we need to apply the cell pressure. Okay, this cell pressure that we apply is similar to the stress that the soils experience in the ground. Okay, do you still remember? Hence, collection of undisturbed soil sample or sample with minimal disturbance is an important consideration in geotechnical engineering. So always choose the minimal disturbance soil sample. Otherwise, your result may not be correct. Okay, so it can, if you use the wrong parameters, then you got the wrong answer. If the wrong answer is in the unsafe side, okay, salah. Tapi you design, then it give you the under predictions of the factor of safety, and it's still okay. But if it gives the over prediction of the factor of safety, then it become problems. Okay, so we want our design to be safe, right? So factor of safety that we can get, try to be more conservative, right? So if you get the higher factor of safety, but instead the real factor of safety is low, then it can be a problem, dangerous. Okay. Now we'll look at the different definition of shear strength. You have learned about the shear strength, okay, in the soil mechanics. When you learn about effective stress parameter, shear balls, everything. Okay, CU test, UU test, SCD test. Okay, before I talk about this slide, so what is CU test? Okay, anyone tell me what is CU test?
Confined undrained test.
No. The first term is not correct. Try again. Try again. Others?
Consolidated undrained test.
Yeah, consolidated. The first term is for consolidated. Okay, so when we consolidated, we subject the soil to a confined pressure. That's correct. Okay, but the term C is actually the consolidated. So we have consolidated undrained test. We have consolidated drain test. And another one is UU test, right? So UU test stands for unconsolidated undrained test, right? Okay, let's say we have a series of CU tests. Okay, then obtain the following failure envelope. Okay, and then in this result, let's say you have these results. Okay, the artificial anchors that let's say it doesn't have the cohesion. Let's say from here we have a total stress here, or it can be effective stress. Doesn't matter. Okay, so this is a Mohs circle. So this is the shear stress, and this is the normal stress. So what is the shear strength here for this soil? Okay, what is the shear strength of this soil? Okay, strictly speaking, the failure shear stress is this tau FF, which is this one. Okay, the one that occurs along the tangent line here. So the failure point is actually somewhere here. Because we know that the failure plane is actually oriented at the delta F. Okay, and so here will be 2 delta F. So this is the failure plane, and then you fail at this point. Okay, however, if you look at this Mohs circle, the maximum shear stress actually happened here. Right? So the failure strength is actually lower than the maximum shear stress. Okay, it's lower, but this one is a correct one. Okay, this one is a correct one, but this one is not the correct one. But to get this point, it's more difficult, right? Okay. If you don't plot the Mohs circle, we don't know it's here, because after we plot it, then we draw the failure envelope. Then only we know where is the what is the value for this failure strength. Okay? So it is not so convenient. That's why we say it is not so convenient. Okay? So we have the structural result. If you want to get the C prime and V primes, we cannot get it until we plot the Mohs circle, right? Okay. Another important note is the above definition of shear strength is consistent with the Mohr-Coulomb model, as is used in many computer programs to calculate if and when plastic yielding occurs for a soil element subjected to a set of triaxial stresses. Okay, so normally we will use this Mohs circle type of failure diagram in the Mohr-Coulomb model. Okay, we will talk about Mohr-Coulomb model later on. Okay, in the end of this chapter. Mohr-Coulomb model basically is the elastic perfectly plastic model. So in this model, we have an elastic part and we also have plastic. So elastic part is defined using the Hooke's law, but the plastic part is actually described using the C prime and V prime values. So it will tell us when the soil fill. Okay, so if you use the Mohr-Coulomb model, then you can tell the computer, okay, these materials will fail at what stresses, because it has the shear strength parameter C prime and V prime, right? Okay. Okay. Again, just now I mentioned that if we want to get this point, this is not so straightforward because we need to plot the Mohs circle first. Okay, especially we need a series of Mohs circle, then only we can get the correct Mohr-Coulomb failure envelope. But if you want to find the shear stress maximum point here, it's easier, right? We have a results, triaxial results, and we can have a confined pressure. We can have this axial stress. Then we can find the maximum point here easily. You just take sigma 1 plus sigma 3 divided by 2. Minus sigma 1 minus sigma 3 divided by 2. Then you can get the shear stress already. Okay. However, unless we do a series of tests, we may not be able to obtain CFE. Okay, if we do not have a CFE, then we cannot obtain the point of tangency of the failure envelope with the Mohr circle. Okay, that's what I mentioned just now. So, we need, if you want to get a CFE, we need a series of triaxial tests, at least 3 samples, right? To get the 3 samples, you need to plot it. You need to conduct the triaxial test for 3 different samples under 3 confined pressure. Okay. Hence, you will find that in practice, when most engineers interpret the value of shear strength from triaxial test, it is usually computed as SD or SU. SD refer to the drain strength. SU refer to undrained strength. Okay. So let's say we have only one triaxial sample result. So we can take sigma 1 minus sigma 3 divided by 2, then that will be the shear strength parameter, shear strength value directly. Okay. It's not parameter, but shear strength value. Okay. So, but here you can see that the shear strength that we take is actually the radius here, which is the maximum point here, maximum value. Okay. It is seldom defined rigorously as the shear stress at the point of tangency between the C fine line and the Mohr circle. So, since we have only one stress sample, then you want to find the shear strength become difficult. So, in practice, sometimes people just use this. Okay, it's simple. Okay, but however, they have a relationship. Okay, you can actually get the SD, the drain strength or undrained strength, using this some simple expression. Now we just now we look at the drain strength first. Drain strength. Okay, you can actually predict the drain strength if you have the friction angle. Okay, for this soil with the equation, effective equation 0, then the expression is very simple. Okay, so sine P is actually the SD divided by this one. So sine kan, sini bagi dengan sini. So SD divided by sigma C plus SD. Bagian sini lah. Okay. So equal to sine phi. So then SD will equal to sigma C prime times S phi, sine phi, divided by 1 minus sine phi. So if we have a friction angle, we have the confined pressure, then we can find the drain strength easily. We can get the drain strength. But remember that the drain strength that we get is actually this point. This point, yang atas ni, bukan sini, yang rendah, yang tinggi ni, bukan yang rendah. Yang actual sepatutnya di sini. Okay, but you can see that the difference is quite small, maybe 10% difference or 5% difference only. Okay, so it's very quick if you want to calculate. Okay, kalau nak suruh cari sini lebih lambat. Okay, what is the shear stress? To find this, then it will be more difficult to find this point. Okay, unless you plot it in the graph paper, then you can see that. You don't plot it, you tak tahu value ni apa. Okay. Now, one exercise, very simple exercise. A normally consolidated clay has C prime equal to 0 and phi prime equal to 28 degrees. The soil is consolidated to an effective soil pressure of 120 kilonewton per meter square, kilopascal, and shear under drain conditions. At what divited stress will the soil fail? Okay, what is divited stress? Divited stress is sigma 1 minus sigma 3. So divited stress is sigma 1 minus sigma 3. Okay, sama juga kalau you tulis dalam effective stress, sigma 1 prime minus sigma 3 prime, sama value saja. Okay, so divited stress. Okay, so here to here, okay, the diameter is actually the divited stress. So the radius is actually the drain strength. So you can find the drain strength. After that, you multiply by 2, then you get the divited stress. Okay, try this one and see whether you can get the answer. Okay, can you get this one? 212. Students?
Yes.
Okay, boleh
Boleh.
Okay, now we move to another the same drain strength, but this time we have this C prime, C terms, cohesion term. So sine phi, you get SD divided by this one, this the whole part here. So we have three components here, which is the C prime times cotangent T plus this is cell pressure sigma C plus the SD and the drain strength SD. So SD divided by whole these three component equal to sine phi. So you do some mathematical arrangement. You arrange. Okay, very simple. You can do by yourself, maybe 1 minute, finish already. So then you will get this SD equal to cell pressure plus this one, C prime cotangent T, then times the sine phi over minus sine phi. So there's only additional terms here, right? If compared to the previous one. Okay, the previous one only sigma C, which is cell pressure. And then here we have another term, which is the cohesion term here. Tambah ini saja. So that's why if you have friction angles or the materials, okay, and the cell pressure, then you can know what is the shear strength of the soil. Okay, this is drain strength. Remember this drain. Okay, drain strength. Okay, you need to differentiate the drain and undrain. Drain strength is normally for the when the soil subject to the very slow loading. Loading is slow, or the soil is cohesionless. Okay, cohesionless, like the sand. When we talk about the sand, normally the strength that we get is drain strength. Okay, meaning that there's no pore water pressure built up when the soil is subjected to loading. Okay, so that's drain. Undrained meaning that the soil is subject to very fast loading. Okay, loading is applied fast, and then there's excess pore water pressure built up. Then that's undrained strength. Okay. Now we look at the undrained strength. Okay, the relationship between undrained strength and friction angle. Okay, now we talk about the drain strength. Now we go to undrained strength. So in undrained strength, like the CU test, CU test, if you conduct a CU test, you get the total stress mole circle and effective stress mole circle. So the difference is pore water pressure, because we know that total stress minus pore water pressure, you get effective stress. Okay, total stress, let's say sigma 3 here, minus the pore pressure, you get the sigma 3 prime here. Okay, so the difference is actually pore water pressure. Okay, now the question is we need to find the SU, the SU here. Let's say if we have the friction angle, can we find the SU? Yes, because you look at here, this mole circle is actually touching the effective stress mole failure envelope. Okay, this touching line is actually the same as the drain test mole circle. Okay, but if you conduct the drain test, okay, you will feel at a higher point. Okay, higher point here, or you can see here now. If drain stress and drain strength is here, but for undrained strength is here. However, both will touch on this failure envelope. Okay, this is mole circle, mole Coulomb failure envelope. Okay, categorized by the friction angle. So dia akan feel pada sini. Kalau betul-betul sepatutnya dia shear strength di sini untuk drain, untuk undrain di sini. Okay, tapi sekarang kita nak cari yang senang faham punya, mana dia adalah maximum di sini. Okay. So that's why these two are related, meaning that we can use the friction angle, effective friction angle, to find the undrained strength. Okay, we can find the undrained shear strength using the effective stress parameter. Nampak? So kalau kita ada effective stress parameter atau drain strength, drain punya effective stress parameter, okay, kita boleh cari undrained punya value, undrained punya strength. Right? So how to do that? Okay. For soil with C prime equal to 0, in this case, let's say the C is 0. Okay. And then noting that A is actually the pore pressure parameter. Pore pressure parameter. We will learn about this later on. Okay. You do the pressure test, and there are two parameters involved, which is A parameter and B parameter. A is related to the soil types. Okay. Soil type more, and also the condition of the soil also. So this A value is actually changing. Okay. So the formula is actually the pore pressure divided by the divider stress. And we know that the divider stress is 2 times the SU. Okay, you can see here, 2 times the SU, right? 2 radius. Yeah. So this A value, we will talk about it later on. If you look at the slide later on, A is actually, the formula is this one. Okay, but you can see from here, it's actually, the pore pressure is actually influenced by the B parameter and A parameter. B parameter is related to the saturation of the soil material, and A material is actually depends on different condition. It can be sand, clay, different type of material also will give you different A parameter. So this is a function of soil properties and stress history. So it can vary from negative to positive. So this value is highly variable. Highly variable. Okay, it depends on the type of soil. Okay, so we'll come back to this later on, maybe tomorrow, no, next week. Just now, you just remember the formula. The formula for A, which is pore pressure divided by Q, which is divider stress. Okay, remember this first. So, how to relate the friction angle with the undrained shear strength? So, you can take the sine phi, which is this one, sine phi sini adalah SU bagi dengan bahagian sini kan, which is the sigma 3 plus the SU. And we know that this is internal effective stress. So if you write in terms of total stress, we will take the total stress minus pore water pressure. Okay. And then we know that the pore water pressure is A times the 2 SU. Yeah, okay, so we rearrange and rearrange again, then finally we'll get this one. Okay, you can try yourself, very easy only. So that's the additional terms here, 1 minus 2AF. Okay, this is A skeleton parameter A. So it's actually influenced by the pore pressure. Okay, pore pressure or pore water pressure. 1 minus 2A. So you compare with the drain strength. This is the additional terms only, 1 minus 2A. Sebelum tu tak ada. Okay, before that is only 1 minus sine phi for the drain strength. Okay, for the undrained strength, you have additional component here, which is 1 minus 2A. Okay, so these A parameters actually affect the undrained strength. Okay, and always remember that the drain strength is always higher than undrained strength. Okay, drain strength is always higher. So if, let's say if you have the footing, okay, you test the footing very fast using very high. Let's say you test it fast, okay, you tekan dia sampai dia feel, okay, then it will feel faster. But if you tekan dia slowly, very slow, okay, very slow, okay, let's say for the soft clay one, then you get you find it difficult to feel it, more difficult compared to when you apply instantaneous loading or fast loading. That's why drain strength is higher than undrained strength. Okay. You see here, they are actually falling. If you use the same confined pressure, okay, same confined pressure. If you do the undrained test, okay, you get the this effective stress Mohs circle. You do the ring test, Mohs circle will get bigger. And this is also effective stress. Okay, and these both effective stress Mohs circle, they are touching the same failure envelope. And this failure envelope, you can use this phi prime okay, to describe this failure envelope. Another one is having the C, C cohesion, okay, cohesion. So you have more samples, then you can get this cohesion. Okay. Normally you need 3 to get the proper actual failure envelope touching the tendency of all these Mohs circle. So same also for this type of soil, non-zero friction angle and non-zero cohesion. Then additional term is this one, C cotangent phi prime. Okay, C cotangent phi prime. Okay, this is how you get the drain strength and undrained strength if you have the friction angles and also some these A parameters. Okay, very simple. Okay, so this meaning that you can actually predict the strength for the soil, and you can use this strength for the design if you know the friction angle of the soil. Okay. And also the normal stress of the soil. Okay, you have to remember that with the soil is deeper, meaning that this confined pressure is higher. So when the confined pressure is higher, okay, then you will get a higher shear strength value. Okay? In this case, higher undrained strength. Okay, when the soil goes deeper, the undrained strength also will go higher. Okay, boleh?
Boleh, sir.
Can, sir.
Okay, if you have no questions, I will continue lah. Okay, I will talk about stress path. Okay, previously we have represented state of stress by a Mohs circle. Okay, this Mohs circle is normally we plot in the shear stress over normal stress coordinate system, right? Look at this one, shear stress over normal stress, tau over sigma. Okay, tau versus sigma coordinate system. Sometimes it is convenient to represent that state of stress by a stress point. So sometimes if you use a stress point to tell the stress state of the soil, it's more convenient because we can see that how it's actually how the soil feel and where and when it will feel and how it feel actually. Okay, later on we'll talk deeper about this, but now bear with me. The stress point has a coordinate of sigma 1 minus sigma 3 over 2. You see here, sigma 1 minus sigma 3 over 2, which is the divider stress divided by 2. And this is also, tengok sigma 1 minus sigma 3 bagi dengan 2. Kalau tengok Mohs circle, dia adalah Y. It's like this one minus this one divided by 2, which is the radius of the Mohs circle, radius. So it means the point here, the highest point here. And the another one is sigma 1 plus sigma 3 divided by 2. So sigma 1 plus sigma 3 divided by 2, maksudnya tengah-tengah sini. So coordinate system, it means that the stress point is actually the peak of the Mohs circle point. Mohs circle, the peak of the Mohs circle. Okay, so the peak of the Mohs circle. Okay, let's say if you have a Mohs circle, right? When stressor test subject to the highest stress, when we increase the stress, the Mohs circle actually get bigger. So we can connect the stress point together, which is the peak of each Mohs circle, and you get a straight line method 2. Okay? So this is what called the stress path. Okay? If you plot in the T and S and T coordinate, this is the stress path. And this is the stress path. Okay? Before we go to that, again, sigma 1 minus sigma 3 over 2 is at the y-axis. Sigma 1 plus sigma 3 is on the x-axis. You can also write in terms of V and H. V means vertical, H means horizontal. Okay, vertical stress, horizontal stress. Okay, or sigma 1, sigma 3. Okay, sama aja. Okay, dalam kita punya triaxial test. For simplicity, define S and T. So we will define this coordinate system, this coordinate using S and T. Okay. Where the T is a sigma V minus sigma H over 2 atau sigma 1 minus sigma 3 over 2. S is sigma V plus sigma H over 2. Okay. Atau kita panggil sigma 1 campur sigma 3 bagi dengan 2. So T tolak, S campur. Ingat, T is considered positive when the sigma V is larger than H. So when the sigma V is larger than H, then you get positive value. Otherwise, you will get negative value. Right? Often, we want to show successive states of stress which a test specimen or typical element in the field undergoes during loading or unloading. We want to see how the stress state, the stress state of the soil. Ini dekat mana, sudah feel ke belum feel lagi? Bila dia akan feel? So you can use the stress path to tell. One way is to use a diagram showing the successive state with a series of mole circles. So we know that the mole circle increase, the stress path will go like this. Okay. For example, a triaxial test with constant sigma 3 and increasing sigma 1, you see? Okay. Because the sigma 3 is constant in triaxial test. Okay. We first consolidate, after we consolidate, we shear. Okay. But when we shear, we don't apply additional sigma 3. Okay. The stress is only applied in the vertical direction, which is sigma 1. So sigma 3 constant saja, dia tak tambah. Sigma 1 tambah. So you can nampak mole circle semakin besar dalam triaxial test. Okay. Dalam triaxial test, mole circle semakin besar. So the stress path looks look like this, 45 degree. Okay, and start from here, where the T is 0 here. Okay, T is 0. T is 0 because the sigma V and sigma H is the same. Okay, kalau sigma V dengan sigma H sama, okay, which is this one. Initially when they are same, then you take sigma V minus sigma H divided by 2, you will get 0, right, for T. So you will start from 0 point here. Okay. Initial point is 0. Okay. Sigma V minus sigma H. Kerana V dan H sama dalam conventional triaxial test, you get 0 for the T. So the initial point is somewhere here. Okay. For the S is sigma V campur sigma H. And sigma H is similar to sigma V, so you have 2 sigma V divided by H, right? So sama je lah. Divide by 2, so you will get the sigma V. Basically, the stress path initially you will be at here, okay? And then the T is 0, S ada value, T is ada kosong, S ada value. Initially di sini. So when we apply loading, okay, if you apply loading in different directions, you get the different stress path. In triaxial test, just now we have mentioned, you go like this, 45 degree. That's triaxial test because we don't apply additional stress for the horizontal, in the horizontal direction. So delta sigma H is 0, meaning that the stress, the sigma 3 is constant, dia tak tambah. Yang tambah hanya vertical stress. So when the delta sigma H is equal to 0, delta sigma V has value, then you get 45 degree. Okay, you can calculate now, very simple only. Okay, so let's say we calculate when delta sigma H equal to 0, what is the delta T or T value? Okay, delta T itu apa? We know that delta T adalah delta sigma V tolak dengan delta sigma H not enough space. Okay, delta T equal to delta sigma V minus delta sigma H divided by 2. Okay, so what is the answer? Delta sigma V, okay, positive. Delta sigma H is 0, right? So you will get delta sigma V over 2 or delta T. Okay, finish. Then we look at the delta S. Delta S is delta sigma V campur delta sigma H divided by 2. And delta V, ada positif, delta sigma H ada kosong. So tolak yang ni. So gradient untuk stress path adalah delta T over delta S. So delta V, jawapan dia sama. So dapatlah 1. Right. But the gradient is 1, the angle is 45. Right. Let's say kita panggil alpha sama dengan tangent tolak 1. So kita dapat 45 degree. Degree ya, bukan nama. Degree. Boleh faham kan? Okay. Now, you try B. Path B. Okay, you try this one. I give you 5 minutes. Try to get B value here. I mean, try to get the gradient for this stress path. Okay, do it now. Okay, finish lah.
Finish sir.
Boleh dapat kan?
Yes, I got it.
Okay, ada yang tak dapat?
No sir, saya tak faham sangat.
Tak faham ah? Okay, let me do for you. Resolve in. Okay, the first thing is to find the T and S. You have to remember the formula. So okay. Pointer. So the change of T, okay, you can put in terms of change of T lah, is equal to delta sigma V tolak dengan delta sigma H, right? Bagi dengan 2. So now we see here delta sigma H is half of the delta sigma V. Okay, maksudnya 1 tolak dengan setengah kan? Kalau 1 tolak setengah, kita tinggal setengah. Atas tu setengah bagi 2, so kita akan dapat 1/4.
Okay, I dah faham dah, saya dapat.
Boleh dapat ha?
Dah.
Okay. So delta S pun sama. Okay. Delta V campur delta H. Okay, 1 campur setengah, maksudnya 3/2. Betul? 3/2 bagi dengan 2, 3/4. 3/4. Delta sigma V. So delta T over delta S, maksudnya dia punya gradient atau slope dia adalah 1/4 delta V divided by 3/4 delta V. So delta V tolak, so L over 1/4 divided by 3/4. So sama dengan
1/3.
So this is a gradient. So cari dia punya angle lah. Okay, I can use the tangent minus 1 to find this angle. So it will be 18.4. Okay, so you can try it for others different condition for different conditions. Okay, if the condition is like so delta sigma H equal to negative delta sigma V, then you will get a straight line, and straight vertical line like that. Okay, but all this is not so common. The common one is this one, C1, because in the triaxial test, the delta sigma H is 0. Because the constant stress, we apply constant stress over the test period. Okay? Only the axial stress is increasing. Okay. Now we look at the stress path in the field. Okay. Consider a solid element at depth H in the field. Okay, we know that in this depth, especially for the vertical stress, it is equal to gamma saturated minus gamma W, right? So that you have the effective stress. Okay. But horizontal stress is, you can find horizontal stress when you have a K0 value. Okay. And this K0 value is the coefficient of lateral earth pressure at rest. And do you still remember when you study the retaining structures, you learn about K0, Ka, and Kv, Kp, and in that topics you have already learned that sigma V and sigma H is not the same. Sigma H is lower than the sigma V. For normal consolidated clay is about half times this separuh daripada vertical stress. So the K0 is 0.5. Okay, you can use this Jackie formula 1 minus psi phi to predict the K0 value. Okay. So you still recall the triaxial test I mentioned just now. The initial stress, our initial conditions is sigma V and sigma H same. But this is not correct in the actual field condition. Okay, in the soil, sigma V and sigma H is different. Right. So if the sigma V and sigma H is different, then you can see that the initial point is not at the horizontal line here. Dia bukan kosong, T dia bukan kosong, tapi it has some value. It has some value. The initial point has some value already. Okay. Dia bukan kosong, T dia bukan kosong. Kerana sigma V dia lebih besar daripada sigma H dia. Okay, and this K0 value is actually quite different for different type of soil. Okay, for over consolidated soil and very dense sand, you can get the K0 more than 1. Okay. Okay, now if let's say the initial point is here, what will happen when we apply the drain loading into the soil? Okay, we apply the loading slowly, so that no excess pore pressure is built up. Okay, so what will happen? Now we look at this one. Okay. Let's say we apply the loading in the vertical direction only. So the horizontal stress remain constant. So there's only the increase in the vertical stress, delta V. So delta V increase. So the initial point is here. So you apply the loading when the delta sigma V increase. Okay. Then it will go 45 degrees going up. Then it will eventually fill. It will fill at the point when it touches this KF line. And this KF line is related to the mole column envelope, okay, but not the same line. Okay, we'll discuss this later. Okay. There's some relationship between this KF line and mole column envelope. So you can see here, when the soil is subjected to axial stress, it will go 45 degrees. This is for drains, drain test. It goes 45 degrees. Okay. In the drain test, total stress and effective stress is the same. In drain test, total stress and effective stress, they are the same stress path. Kalau drain test, you go 45 degrees, it will touch the field here. When it touch here, we know that the soil, the soil has filled. Okay. At least for this point. Okay. Bahagian sini sudah fill. Okay. Bahagian lain mungkin belum fill, tapi bahagian sini sudah fill, katakan. Okay. For unloading problems, okay, we have a negative delta sigma V, okay, but the sigma H is still remain constant. So this is unloading problem. So kurangkan overburden dia, the excavation happen. So the stress path will go this direction. And eventually you will fail also. Okay, you will fail also. So this is an example of stress path in the field. Okay, there are different stress path, different behavior for different application, okay, and different type of soil. But this is what we call the simplification. Okay, simplification. Secara general saja untuk yang axial loading and unloading case. Okay. So until now, do you have any questions? I think I will stop here. I will leave the traxia stress path for it maybe next week. If any question to ask regarding the today lecture?
Sir, can I ask something, sir?
Yeah.
For unloading is normally used for what at site? Basically, they want to excavate for
Excavation.
for building road or embankment, is it?
Excavation. You know excavation, right? It can be excavation building structures, and then you can know the stress path for the soil below the excavation. Below excavation. So loading is very straightforward. It can be footing problem, right? Footing. But for this unloading, it can be excavation, meaning that we remove the axial stress. Okay. But in the real application, it's not that straightforward. This is very simple example where we have a large area excavation. But in the geotechnical application, like the retaining structures, it's not like that. It is quite it's more complicated. But this is a general form. where the excavation we consider the whole area excavate. Okay. Yang ni bahagian bawah saja, bahagian bawah excavation. So it may look like this. It look like this. Okay. So this is for the drain loading. I remember drain loading. Okay. However, it's very difficult to fill the soil in. In this case. Okay. It goes to this. Okay, but normally we don't say that the soil has filled when this has a what we call the excavation process. Atas correct, unloading berlaku. Okay, tapi bila unloading berlaku, walaupun dia nampak macam dia pergi ke arah ini, sebenarnya tanah itu dia tak kira fill sebenarnya. Okay, kita cakap dia touch ni extension line saja. Failure line is more to the compression because the soil itself is what we call it. It has a very low tensile strength. Okay, it has a very low tensile strength. Okay, so you can say that you want to fill a soil in the tensile direction. It's very easy to happen, but it has not much significance if you do the excavation for a very big area, but it has a very big significance when you do the excavation for the retaining structure. Okay. It's okay if you don't understand, but what I want you to understand is that the stress path can tell you where the stress will go. Okay, but for the axial cases, loading case, you go like this and you will fill. And this one will tell you that the slope, the soil at that point has filled. Okay. So this is the common failure for the loading. Unloading failure is not so common. Okay. Unloading failure is not so common. If you have a excavation a deep excavation, you excavate the soil will rebound, right? It will rebound, and then when it rebound, you can see that the stress path actually go to these directions. Okay, it may not fill, but it's really approaching the extension line. Okay, extension line. But if the excavation is too much, it seems like it has lost contact with each other. Dia macam sudah tak sentuh antara satu sama lain, tapi sebenarnya dia masih sentuh lagi. Dia tak ada kes di mana tanah itu tak sentuh. Okay, dia masih sentuh, tapi dia sudah dekat dengan tak sentuh, macam tu aja lah. Kerana dia rebound. Masih lagi sentuh lagi. That's why you want to fill the soil in the tension. It's very easy. You ambil soil, kadang-kadang dia triaxial punya kan, you cabut macam tu je, dia senang fill kan. Tapi bila you nak tekan dia susah fill sikit. Tapi sebenarnya benda tu tak begitu we call that important when we are talking about the large excavation area. Okay, because we are going to fill the soil in the loading is normally applied from the top, right? Okay, and then the failure is normally under compression. Okay, even though it looks like that is going to fill, but actually the soil doesn't feel like that. Okay, this is for very simple. For simplicity only.
Okay, sir. I see that. Thank you very much, sir, for explanation.
Yeah. So that will be a bit more difficult to understand, but it's okay. Okay. We'll talk about the easy problem first, which is triaxial. Okay. Even though it looks easy, but it can be quite complicated if you don't follow my slide here. Okay. So better that you study before you come to class. So today we will talk about the elastic behavior using Hooke's law, and then we also talk about the plane strain and plane stress. Okay, and then we will also talk about the shear strength. Shear strength, how to get the shear strength from the shear strength parameter like the C prime and V prime. Okay. And then we will also talk about the stress path. So that's all for today. I think enough already. So I want you to do some exercise on the problem set. Okay, look at the problem set and do some exercise. Okay, so that's all for today. No question, right? No question. It's time to say bye-bye. So you can leave
No,
now.
sir.
Okay, sir. Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir. Thank
Okay,
you, sir.
bye-bye.